Okay, so we are on 2.3F. We are not doing 2.3E. This is our last section before our quiz. And this is about two-body problems. So far, what we've looked at are objects, are single objects. Just one object moving under the influence of Newton's laws. All right, we've looked at one single skydiver falling. We've looked at Yusra pushing one single book across the table, right? We're always looking at one object. Our system that we're looking at has been up to this point only one object that is moving, that we need to determine the acceleration of, that we need to determine the mass of, or the force of, whatever we're looking at. But what if we have two objects connected and moving together? That's what we're going to be looking at with two-body problems. So let's look at an example of that. So the example I have drawn here, and right here, is we have this big truck, and it's connected to this little car. It's towing this little car, and the truck is moving forward. So there's a lot of different things we need to think about when we're looking at these two objects moving, rather than just one car moving, or just the truck moving. So how is the acceleration of the car and the truck? How are they determined? How do we determine acceleration? That's one question. Are they the same? Are they different? Is one going faster? Is one going slower? What about the force acting between? What about this force here? What about this tension force between the car and the truck? What is that? Right? There's lots of different problems or issues or things we can look at with two-body problems. It complicates things a bit more. So in this section, 2.3, we're going to look at these two-body problems, at situations where there's two objects moving together, and we're going to use Newton's laws and free body diagrams to kind of solve these problems like this. So let's look at there's two different ways that we can solve these problems. Let's look at those. All right, so we have two different methods that we can use to solve two-body problems. So we're going to go through the methods first, and then we're going to do some examples using both of these methods. So the first method is where we use what's called a system analysis. And remember, this means system as in like system and surroundings, like I taught you a long while ago. System analysis plus an individual body analysis. We're going to talk about what each of those mean. That's method one. Method two is just two individual body analyses. Oops, I crossed out there. All right, so we're going to talk about how to use that one in a second. So method one involves, like I said, this thing called a system analysis. And the system analysis is going to be used to determine acceleration the majority of the time. So in a system analysis, in this first part of method one, we have two objects that are considered as a single moving object. And we'll have the mass will be equal to just both of the objects' mass added together. And the acceleration, if we don't know it, or if we do know it, if we know one of them, we'll just assume for the whole thing that it's the same as the individual object's acceleration. All right, so that's that's one part, the first part of the method. Then we have the individual body analysis. We isolate one object. So rather than considering them as one object like we do with a system analysis, in an individual body analysis, we're going to isolate one of the objects and treat it as if it's separated from the second object. And we do this in order that what we're solving for when we do the individual body analysis is we're trying to determine the force or forces that act between the two objects. And some examples of the types of forces that we'll see between two objects are contact forces, like applied forces, or tension forces. So we'll have, that's just an example. We could have others, but those are the most common. Applied forces or tension forces. All right. So with this method, we're gonna do an example. I've explained what we do, and now we're going to do an example here. So let me get that up. Okay, so it says a 5 kilogram and a 10 kilogram box are touching each other, like we have drawn over here. Okay, a 45 Newton horizontal force is applied to the 5 kilogram box, so it's getting a force of 45 Newtons horizontally applied to it. In order to accelerate both boxes across the floor, we are going to ignore friction forces, and we're going to determine the acceleration of the boxes and the force acting between the two boxes. So, as I just told you with method 1, the first step of doing method 1, or of applying method 1, is the system analysis. System analysis. So that's what we're going to do first. And remember, the system analysis we're going to use to determine acceleration, and we're going to consider both of the objects as one single moving object. So rather than having this little box and this big box, which are touching each other, rather than having two separate objects here, we're going to pretend like this is just one object for the first part of method 1 with the system analysis section. Therefore, let's determine what the mass of this single object is. Remember, this little box was 5 kilograms, and this big box is 10 kilograms. Well, now that we've combined them and made them one, the mass of this will be 15 kilograms. All right, so let's move this guy down a little bit. Move him down here. Let's draw this as a free body diagram. Let's think about all the forces acting on this quote-unquote single object. Okay? All right, so just like with any object on Earth, we have the force of gravity. We have the normal force. And remember, we said that there was an applied force. This guy, see this guy's hand pushing on the box. So it's an applied force. We'll say that it's to the right. And it's on the whole system now. We're not breaking it up into two boxes. Now it's on the entire system. Okay, so we would draw it like this. This would be the free body diagram for this singular object that we're moving. And we can actually give this one a value. We said this was 45 newtons. Okay, we also said that, was there any? No. There is technically a force acting here between these two boxes, right? But this is what's called an internal force. Internal force. Because now we've made it, for this situation when we're doing a system analysis, it's an internal force because it's technically, with the lens that we're looking at this through, it's technically inside of our single object that we've kind of made this boundary around, right? So we're going to ignore any forces that it might exist right here for this first part when we're doing our systems analysis. All right, so now we can determine the acceleration of our object. We already know our mass. We know, let's write our knowns and unknowns here. All right, our mass, we added those two together to get 15 kilograms. Our force, what is the force? What is the force being applied to this singular object? It's 45 newtons. And we're looking for our acceleration. Remember, we're going to assume that this is all just one object, so the acceleration of one, the one object can be applied to both objects. So we're going to use our equation F equals m times a, but we're going to rearrange it for a. So we have acceleration equals force divided by mass. Now we can solve. And we get acceleration equals 45 newtons divided by 15 kilograms. This gives us an acceleration of 3.0 meters per second squared. Okay, so now that we've determined our acceleration, we're done with the first part of our method 1. So we got our acceleration. Now we can go on to the second part of method 1, which, remember, is the individual body or individual object analysis. So let's get rid of this. So we are going to do this individual body analysis, and we can do it on either of the two objects in order to determine the force that's acting between them. So remember, we have these two objects. Now we're going to draw them as two objects. We're going to consider them separate. We have our 5 kilogram little box and our 10 kilogram big box. So it doesn't matter which one I choose. I just am going to choose one of them in order to determine the force that's acting between them, because there is a force acting there between them. Remember, a force is a push or a pull. So there is a force acting between these two boxes. So now we're going to use the individual body analysis to determine what that force is there. So we are just going to choose the 10 kilogram box. We're going to use it to draw our free body diagram and to determine the force acting between these two boxes. So let's move this down here. All right, so let's think about the forces acting on this. We have the normal force, we have a force of gravity, and we have a contact force, because this isn't, you could call this an applied force too, because the 5 kilogram box is technically having the applied force to it, so it would be better to call this a contact force, right? But technically it is an applied force too. The online book says that this is a contact force, but I would also consider it an applied force. Okay, so these are all the forces acting on our 10 kilogram box. All right, so we know that, let's think about our net force acting on this object. We know that the F normal and the force of gravity, they're going to cancel each other out, right? So we're not even going to consider them as part of our net force. So the only net force that is actually here is this contact or applied force from the 5 kilogram box. So the F net is going to be equal to that, whatever that contact force is. Remember, because we said we were ignoring friction. Technically, in the real world, we wouldn't ignore friction. But anyway, so what does F net equal? What is an equation that we know for F net, or net force? We know that force or net force equals mass times acceleration. Well, from part 1 of method 1, we determined the acceleration, right? We know acceleration. Do I know the mass of this box? Yes, I do. So I know the two things that I need in order to solve for this net force, or to solve for this contact force, which is the force occurring between the 5 kilogram box and the 10 kilogram box. So if F contact is the same thing as net force, I could say that contact force equals mass times acceleration. And I already know the mass, I already know the acceleration, so all I have to do is plug that in and solve for it. So let's do that. Our contact force is equal to the mass, which is 10 kilograms, times the acceleration, which we solved for earlier. So our contact force, the force that's acting between the two boxes, is 30 newtons. The force that exists here, if I redraw that other 5 kilogram box in here, the force that exists right here is 30 newtons. All right, so there you go. Method 1, we solved first for acceleration, then we solved for the force between the two objects. So that's going to be the general gist. When you use method 1, you're going to first solve for acceleration, then you're going to solve for the force between the two objects. The way that we solved for acceleration was by assuming that this was one object, right? We made it one object instead of two objects. That was the system analysis. And then the individual body analysis, we looked at just one of the boxes or one of the objects, and then we used that in order to determine the force that's acting between the two objects. All right? So there were two unknowns and we solved for both of them. So that's the first method. That's the way we can use the first method. Now let's look at method 2. All right, remember that method 2 is basically just two individual body analyses together. So now we're going to just cut out that first part of method 1 where we did a system analysis and we assumed that the whole thing was one object. We're not going to do that. This time we're just going to look at the two objects as individuals. We're going to have two different free body diagrams. We're going to have two different calculations we have to do. Well, we're going to use Newton's laws for both of them. So there is a summary of what we're going to do with the individual the two individual body analyses. So let's look at that same problem that we just did. We're going to look at that same problem, but we're going to apply method 2 to it instead of method 1 like we just did. So we're going to pretend that we don't know the answers to acceleration or mass. So let's draw both of the free body diagrams for the individual objects because that's the first part of using the second method here. All right, so we're going to take these two and we're going to draw a free body diagram for the 5 kilogram. And we're going to draw a free body diagram for the 10 kilogram box. All right, so for the 5 kilogram, we have a normal force. We have a gravitational force. We can actually solve for Fg if we wanted to give this a value, but we don't really need to give it a value. We know that we could just plug it in and do mass times the force of gravity, and we'd get about 40, 50-ish newtons. But anyway, we don't need to do that. All right, but we also have an applied force to the right of 45 newtons. Oh, that's applied. And we have a contact force because where the boxes here are touching, there is force there. There's a contact, there's a force. So remember for every, do we know that yet? No, we haven't gotten to that law yet. Well, this box isn't moving through, the 5 kilogram box isn't moving through the 10 kilogram box, right? So just like the normal force and the gravitational force, we have to have a force pushing back in the opposite direction of the applied force. Okay, so that is what we have for the first 5 kilogram object. For the 10 kilogram object, we have the same normal, gravitational, and we could solve for those if we wanted to, but we're not going to. And then we have a contact force. Contact, right? This box is pushing back on the applied force that's being, well, you could call this an applied force or a contact force, whichever you want to do. But we're going to call it a contact force for now. Okay. The reason that we're not going to write this as 45 newtons is because we're now treating these two boxes as two individuals. And we're not, think about this hand. This hand is the one that's applying the 45 Newton force. So this contact force is because it's caused by the 45 Newton force, but it's not the applied 45 Newton force. So we're not going to write the applied force twice because then overall it would give us a combined net force of 90 newtons, but that's not right, right? So those are the two free body diagrams for both of these objects, these two individual objects. All right. So now we're going to start trying to solve for some things here. So we want to know the acceleration of the objects. We want to know the force that exists between the two objects. But we're going to do this by using these two individuals rather than looking at them as a whole. So what we're going to look at first is the net force of this first box. The net force is going to be this force, this force, the applied force minus the contact force, right? Because we're not going to take into consideration these two forces because they're balanced, all right? So the net force is 45 newtons minus whatever the contact force is. We don't know what the contact force is yet, all right? Okay, so we know that F net also equals mass times acceleration. So F net is the same thing as this, is the same thing as this, right? So what we can do is combine these two equations to say that 45 newtons minus the contact force is equal to mass times acceleration. Well, we know mass already, so we can actually put 5 in there, right? 5 kilograms. All right. So unfortunately, we have two unknowns. We don't know the contact force. We don't know the acceleration. We're pretending like we don't know. So we are done for right now. So we're going to stop there for the first free body diagram. Now let's look at the information given to us for the second free body diagram. What is the net force acting on this object? We're not going to take into consideration the vertical forces because they're balanced. So there's no opposing net force this way. So the net force for the second individual body here is just F contact. They're equal, right? Well, we also know that net force, same thing, is equal to mass times acceleration. So we can say that F contact equals mass times acceleration. We already know mass for this object is 10 kilograms, right? Okay, we're stuck here again with two unknowns. We don't know our contact force. We don't know our acceleration. Okay, so now that we're here, we have two unknowns for each of these equations. But let's think about something really quick. Will the contact force here be the same as the contact force here? Yes, the contact forces are going to be balanced out, right? The contact force is just the force between those two objects, right? It's this force. This is the contact force. So it's the same thing. So what we can do is we can take this F contact that we just solved for, and we can plug that in right here where we have another F contact. So now we're going to kind of combine these two equations with two unknowns that we just solved for, and we're going to use those in order to find the acceleration. So if I take this value and plug it in for F contact over here, I will get 45 newtons minus this, which is, I can just write 10. I'm going to stop writing units because it can get a little confusing. So 10 times A is equal to 5 times A. All right. This is just basic algebraic rearrangement that you definitely know how to do. I'm going to rewrite this so that you can see what I mean. I have 45 newtons, and again, I'm not going to write units anymore. 45 minus 10A equals 5A. How could I rearrange this to solve for A? Well, I could subtract 5A from this side, subtract 5A from this side. When I do that, actually, why am I doing this so complicated? Let's add 10A to both sides. That will make it, let's not deal with the negatives. That's way too complicated, sorry. Let's rewrite 45 minus 10A equals 5A. Rather than subtracting 5A, let's just add 10A. If I add 10A to both sides, I cancel out my 10A here. I have 45 equals 15A, right? This is the same thing as, you could even think of this as 10x, right? This is 10x and 5x, right? We just have a different variable here. All right, so now I have 45 equals 15A. To isolate A, I divide both sides by 15. And I get that acceleration equals 3.0. I know that my units are meters per second squared because I'm talking about acceleration. Woo! Okay, so that is the way that we can solve for acceleration for the second step. So it involves, first, we need to figure out, we look at our net forces for each. Then from there, we can come up with kind of an equation relating our two unknowns, which are our net force, or we've replaced with contact force in this situation, and acceleration. Then for the other one, we do the same thing. We did the exact same thing, but then we took that equation, or that value for F contact, and we plugged it in for our first equation. Then from there, we just did some basic algebra, and we were able to solve for acceleration equaling 3.0 meters per second squared. All right, the last step of this, because now we know acceleration, but we still don't know the force between them. So what we're going to do is we're going to take our acceleration that we know, and we're going to use it in order to determine the contact force. So all I literally have to do here is just take this equation, F contact equals, we'll just use 10 kilograms times A, which I just solved for, is to be 3 meters per second squared. If I multiply 10 times 3, I get an F contact equal to 30 newtons. So that last part is super simple. We just have to, we could also have plugged it in, you could have plugged it into this equation, but that's way messier to deal with, so I just plug it into our F contact equation that we wrote initially. All right, so that's the second way, that's the second method. Let's look at one more example. All right, here's our second example. We have this is the same kind of example I started this lesson talking about, but here we're going to give it numbers and we're going to use it to the two different methods to solve. So a truck is pulling a car, just exactly the same as the first example. So the truck's mass is 4.00 times 10 to the 3 kilograms, and the car's mass is 1.6 times 10 to the 3 kilograms. The force of propulsion from the truck's turning wheels is 2.5 times 10 to the 4 newtons. We want to determine the acceleration of the car and or the truck, and we want to determine the force at which the truck pulls on the car. We are not going to consider air resistance. Okay, so let's first kind of lay out everything in picture form here. So I have the green car here. Here I have the green car, and its mass I've written next to it. I have the blue truck, and its mass I've written next to it. There's an applied force. Don't be confused by wording. You have to decipher. We have to turn these situations into physics, basically usable physics information. So if the force of the propulsion resulting from the truck's turning wheels is blah, 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 another way of thinking about that is it's the applied force. There's a force being applied onto the truck by the truck's engine, and that force is 2.50 times 10 to the 4 newtons. And that's causing the truck to pull forward. Okay, so let's look first at method 1. How can I solve this using method 1? First and foremost, I'm going to use the system analysis. Remember, I do the system analysis first, where I look at these two as one object. Then I'm going to do first, second, then I'm going to do an individual body analysis. All right. So, first, system analysis. Let's say that this is my car and my truck. They are one object moving together. Okay? There's my object. I have a normal force, of course. I have a force of gravity. The car and the truck are not moving vertically, so I'm not going to waste our time solving for them. in the homework, I think I do ask you to solve for them, but that's easy. All we have to do is mass times gravity. Remember, the mass, because this is one individual system now, we have to take the mass of the car and the mass of the truck in order to determine that. So it would be 1.6 times 10 to the 3 plus 4.0 times 10 to the 3, and then we'd multiply that by our force of gravity. And of course that's going to be equal to the normal force, because again, this is these are balanced forces. They're vertical balanced forces. The truck and the car aren't moving up and down. All right, but we're not done. We have one more force on this object, and that is an applied force of 2.50 times 10 to the 4 newtons. We also have another force in there, this force here, but because, again, we're going to ignore it, we're considering that an internal force existing inside our singular object here. So we ignore that internal force right now when we're doing our system analysis. So this is it. This is the free body diagram if we're just looking at this situation as one object. All right. So from this, what can we say is the net force? Well, we're not looking at these, right? We only look at the horizontal forces because there's only horizontal movement. So the net force is going to actually just be equal to the applied force in this situation, right? So the net force, F net, is equal to 2.50 times 10 to the 4 newtons. We know that we use the system analysis to solve for acceleration. We don't know the acceleration. We don't know how fast this is going. So what we need to do is use the things that we know. We just found our net force. Well, we know our net force now. Is this. We also know our mass. Remember, with a system analysis, the mass of this one plus the mass of the truck, the car and the truck, that's the total mass of the system now. So we need to add these two together in order to determine what they are. So it's going to be 5.60 times 10 to the 3 kilograms. Our unknown is our acceleration, and our equation is the one we've been using. It's just Newton's second law equation, and we'll rearrange to solve for acceleration. So we get acceleration equals net force divided by mass. Plug everything in and solve. We get acceleration equals and if I plug that into the calculator, I get that my acceleration of my two objects is 4.4, and we have three significant figures, 4.46 meters per second squared. Cool. All right, there. I have done my first step in solving for acceleration using the system analysis. Now I'm going to do an individual body analysis to determine this force that exists between this force right here that is acting between the car and the truck. So to do that, we don't need our system analysis free body diagram anymore. We are going to draw a free body diagram for just one of the two objects. I'm going to choose to draw it for the car. So we have our normal force, we have our force of gravity. Now, what other forces do we have acting on the truck? Or excuse me, on the car. We're doing the car. Well, we cannot say that the car has the applied force acting on it, because the applied force that we had earlier is coming from the engine of the truck. So we don't call this an applied force here, but there is a force between the truck and the car, and we can call that either truck car force. Or if you want to be actually correct, it's technically a tension force, right? Because there's some kind of cable or chain or something, whatever it is, between the car and the truck. So we can call it the truck car force or the tension force, whatever you feel more comfortable calling it. I will understand what you mean. So that tension force is the force that's pulling the car forward. It's coming from the truck, but it's not the applied force that is in the truck's engine or that comes from the truck's engine. All right, so what is the net force acting on the car? The net force is going to be, we don't have any vertical movement, so the net force is going to be equal to the tension force, right? Well, another way of saying that is net force is equal to mass times acceleration, right? So we already know our mass for the car is 1.6 times 10 to the 3 kilograms, and we just solved for our acceleration, which I deleted, but remember was 4.46 meters per second squared. That's our net force. That's another way that we can solve for net force. And since net force and tension force are equal to each other, we can say that the tension force, or the truck car force, is equal to the same thing, right? We just take this and put it there because they're equal. All right, and when we do this, when we plug this in, we get that the tension force, or the force between the truck and the car, is equal to 7,100 and we only have 3 significant figures, 40 newtons. If you plug that into the calculator, that's what you will get. All right, so that's the first method. I think that is where I'll stop today. And because the second method, you need to understand that there are 2 ways to solve these problems, but I also feel like the second method is a lot more algebra, and you would probably feel more comfortable using just the first method to solve for these things. And there's never going to be a time where you have to use the second method, so I'm going to stop here like this for the first method, or just using the first method. If you want to use the second method to solve these problems in your homework and whatever, that's awesome and that's great. If that's the one you're more comfortable with, you can totally do that. But I feel like most of you will probably be more comfortable doing the first method rather than the second. So this is where we'll stop for today. You have some homework problems that will be due before the start of class. The late policy will not apply to those, meaning if you don't hand them in tomorrow morning before 9:53 a.m., they will be counted as a 0, even if you are working from home. They're due at 9:53. I'm going to go over them in the lecture video. So you must finish them by tomorrow, the start of class. And we are very close to finished. Tomorrow we will be done with 2.3F. So I have to decide if I'm going to have a 2.3 quiz or if I'm going to combine it with the 2.4 quiz. I think that's what I actually will do. We'll have a 2.3, 2.4 quiz, and that will be coming up in the next probably 2 weeks. And then you'll have a unit exam on 2.1 and 2.2, 2.3 and 2.4. All right? So we're done with 2.3. We'll go over it a little bit tomorrow, and you will start on 2.4 on Friday, I believe. Please let me know if you have any questions. Work on those problems. If you run into some questions on those, please feel free to ask. Thank you.